Welcome back to Math with Ace, focusing on statistics. We are continuing tree diagrams here. We're going to be we have given frequencies in fraction form, and we're going to be using these to determine some probabilities. A litter of kittens available for adoption at the Humane Society has 4 tabbies and 5 black. The family comes in and randomly selects 2 kittens for adoption. Well, they're not going to take a kitten and give it back. They're going to take a kitten and then take another one. So once they've selected one, there's not as many kittens to choose from, okay? So first kitten, they can choose from 9. Second kitten, they choose from 8. How many different combinations is that? 9 times 8 gives you 72, all right? What is the probability that both kittens are tabby? Well, first of all, we have a 4/9 probability for tabby. So A does not have 4/9 listed. That's not going to work for me. But B, C, and D all have 4/9 listed here. But then I need a second tabby, which is 3/8. B has 4/9, D has 4/9, which means they put the kitten back. That's not very nice. C is going to be my answer here. 4/9 times 3/8, which would give us 12 70-seconds. You can actually reduce it. Fine. What is the probability that the one kitten of each color is selected? Now, there's a couple ways you can do this. You can get a black and then a tabby, or you can get a tabby and then a black. And so you need to focus on both of those options. So if we did tabby and then black and then tabby, we need to multiply 4/9 times 5/8 and add that to 5/9 plus 4/8. And we're adding them together because they're mutually exclusive. You can't have tabby blue, or black tabby at the same time, okay? So 4/9 times 5/8. All right, so I'm in business so far here and here, but not C or A. But then B doesn't add on the second way it could happen, which is 5/9 times 4/8. So our answer here is D. Now, what is the probability that a tabby is chosen as the second kitten when a black kitten is chosen as the first? This is conditional. This is saying you chose a black one. What's the probability you chose a tabby? So what is the probability that you chose a tabby given you chose a black cat first? So tabby 2, black 1. Well, let's focus on the black ones. So black first, this is my conditional probability here. The probability of getting a tabby is then 4 out of 8. What is the probability of choosing 2 kittens of the same color? There's multiple ways you can do this. You can get a black kitten and a black kitten, or you can get a tabby and a tabby. So we need to consider both of those options. Here's my tabby tabbies. Here's my black blacks. So tabby and then another tabby, 4/9 times 3/8. And then I need to add that to 5/9 times 4/8. That is 12 70-seconds plus 20 70-seconds, or 32 70-seconds. And I'm not going to reduce it. Okay. Let's move into Venn diagrams. Another way that you can display your data. Suppose an experiment has the outcomes 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, where they're each equally likely. The event A from that sample space is 1, 2, 3, 4, 5, and 6. Event B from that sample space is 6, 7, 8, and 9, which means that events that are in A and B would be 6. Only 6s in both of those. And A or B would be all of A and all of B, but not duplicated. So we're going to make a Venn diagram for this situation. First of all, we need a rectangle because we have our total sample space and we may not have them completely in the Venn diagram. We're going to do a circle for A and we're going to do a circle for B. So this is event A and this is event B. Now, A and B is the intersection where they come together. That's the number 6. That goes in the middle. Everything that's in A that's not shared with B then goes in the circle on the left. That's the numbers 1, 2, 3, 4, and 5. Everything that's in B that's not in A is written in the circle of B. That's not in the intersection. So I have 7, 8, and 9. My outcomes went through 12. So where do I put the 12? I have 10, 11, and 12 in the rectangle because that rectangle is my total sample space. So all the outcomes should be in that Venn diagram. Let's do one more like that. Draw my sample space rectangle, and then draw for my outcomes. These outcomes, we're talking about flipping 2 fair coins. So I'm going to flip 1 coin, and then I'm going to flip a second. A is tails on the first coin, and B is tails on the second coin. So if A is tails on the first coin, I can get tails, tails, or tails, heads. If B is tails on the second coin, I could get heads, tails, or tails, tails. Are there any outcomes in both? They have to be in the same order. HT and TH are not the same. That means that one had tails first and one had it second. So tails, tails is the same. It's in both. So the intersection would be tails, tails, which means that goes in the middle of the Venn diagram where they overlap. Think about if you were to separate the circles, they both need to have tails, tails in them. And then when you merge them, the piece that comes together and has anything is the 2 that are overlapping. Mutually exclusive events don't overlap and don't have anything in common, and they could just be 2 regular circles on their own. Now, or is everything that's in A and everything that's in B, and then you just don't duplicate anything. Well, A was tails, tails, and tails, heads was not in B. B was tails, tails, and heads, tails was not in A. I don't have every single outcome. What about heads, heads? That goes here. That's the complement of A or B. So now I have all of the 4 outcomes possible in my Venn diagram. Come back for our last set on Venn diagrams.